We're going to take a look at dissociation and major entities today. That corresponds to section 5.1 in your textbook. Our goal today is to be able to write ionization and dissociation equations and determine the major entities for ionic, molecular, and acidic compounds. To get started, pause this video and give these 3 questions a try. Describe what happens to crystal lattice when soluble ionic compound is added to water. Draw a picture to describe what happens when solid sodium chloride is added to water. And what is the name of this intermolecular force? So what we know is that a soluble ionic compound, when added to water, the positive ion and the negative ions break apart in the crystal lattice. The positive ion gets surrounded by partial negatives in water, and the negative ion becomes surrounded by the partial positive in water. To describe what happens when sodium chloride is added to water, I've drawn it on the next page here. And by drawn it, I mean actually took a picture from a textbook. So we have the crystal lattice of NaCl. The positives and negatives in that crystal lattice are held together by electrostatic interactions. So a positive and a negative being attracted. That's what's holding the positives and negatives together in the actual lattice itself. Remember, within water, water has hydrogen bonding. So hydrogen bonding is holding the water molecules together. If they were in separate places at this point, that's what we're talking about. When we add it to water, each ion becomes surrounded by water molecules itself. So we had to break all of the electrostatic interactions. We had to break some of the hydrogen bonds. And what we've created is what we call an ion dipole interaction. And this is because an ion, like our positive sodium here, is surrounded by the dipoles of water. So the partial negative, aka the oxygen in water, orients itself to surround the positive. That's because a positive and a negative are attracted, whether it's a full positive and a partial negative or full positive, full negative, whatever it is. Same thing happens with chlorine, except because chlorine is negative, it will be surrounded by the partial positives of water, which are the hydrogens. So again, the interaction between these two is called the ion dipole. Now, water is still there in probably the greatest quantity. So we know that the water is still having some hydrogen bonding interactions. So water molecules are still attracted to other water molecules by hydrogen bonding. So we haven't broken all of the hydrogen bonds, just some of them to make room for these molecules, these ions in between. But we have broken apart every electrostatic interaction within the ionic compound itself. All right, so we're going to look at Arrhenius' theory. Arrhenius proposed that when a substance dissolves, particles of that substance separate from each other and disperse into the solution. We just looked at that with sodium chloride. This determines whether a solution is an electrolyte or a non-electrolyte. We talk about this. An electrolyte means that it conducts electricity. I guess I should write it out because E- is an electron in my world. And a non-electrolyte electrolyte, oh my goodness, doesn't conduct electricity. So, to really understand what's going on in solutions, we need to know what is present in that solution. And so that's where we're looking at major entities. What is there? A dissociation is the separation of ions that occurs when an ionic compound dissolves in water. So we looked at the dissociation of NaCl when it created ion dipole interactions. A dissociation equation, though, is a balanced equation that is showing this separation. So we're starting with NaCl in this case as a solid. And what we're going to do is we're going to show that NaCl creates an Na plus on its own and a Cl minus on its own when we've added them to water. Okay. So again, I don't actually include water in this equation. What we've seen is that we go from a solid to something aqueous. Aqueous means that I've added it to water. So the solid becoming aqueous implies that it's been added to water. I don't include H2O in my equation. For magnesium nitrate, if we were to write magnesium nitrate, we get Mg2+. And if there's multiple of any ion, it becomes a coefficient. They are separate ions. So we get 2 nitrate ions on their own as well, and everything's aqueous. We've balanced the equation. One thing to note, if I'd had something like calcium chloride, so CaCl2 as a solid, I'm going to make a calcium ion, and I'm going to make 2 chlorine ions. Okay, I do not make Cl2 as a gas. We are not making elements, we are making ions, therefore they have a charge. Again, the subscript becomes a coefficient in front. Ionization is when we make a neutral atom or molecule into ions. Okay, so this only happens really with acids in our class. That's all we're going to discuss with them. So, for instance, HCl is an acid, and it's molecular technically because there's 2 nonmetals. However, when I add an acid to water, this molecular compound, it becomes separate ions. And again, this only happens to acids in our class. So we're going to write that HCl creates H plus and Cl minus when added to water. H2SO4. Again, there's 2 hydrogen ions there, so 2 H pluses and an SO4, 2 minus. So don't forget charges and to balance. Last but not least, CH3COOH. This H is the acidic H. Therefore, we're going to make CH3COO minus and an H plus. It doesn't matter the order that you write these two in. I usually just write it in order from the compound before. All right. Again, we made 2 H pluses. We did not make H2 as a gas. That is incorrect. So let's actually write these out for different compounds. So we'll look at ionic compounds first. What we can see is that there are 2 ways to address an ionic compound. We can either decide if it is soluble or insoluble using our solubility table on the back of our periodic table. So what we have is aluminum sulfate. And aluminum sulfate, if you look on the back of your periodic table, is a soluble compound, meaning it will dissolve in water. So if I place this solid into water, it will dissolve into its ions. So we're going to get aluminum, which is a 3+ ion, and it will become aqueous. And we're going to get a sulfate ion, and it will be aqueous as well. Now we need to balance. An equation is always balanced. So there were 2 aluminums in our compound, therefore we are going to get 2 separate aluminum ions. There were 3 sulfates, so we're going to get 3 separate sulfate ions. When we list our major entities, we're just making a list. Okay, what is there? Well, we've added this to water. So here's where water makes its appearance. Water is going to be included in every major entities list. Okay, so you could go ahead and add it to everyone at this point. Now, what else is there? If I were to zoom in on this solution, I would see separate aluminum ions. and I would see sulfate ions. Again, I don't need how many. This is just a list of who is there, not how many of each are there. All right, looking at magnesium carbonate, it is insoluble, looking on the back of our periodic table. Therefore, when I put magnesium carbonate in water, there will be no dissociation equation. So there is no equation. It does not dissolve. If it doesn't dissolve, the major entities, well, I've got water. I tried to add it to water, so water is there. And because it didn't dissolve, it's going to be listed all together. They did not separate into ions. And again, it is still solid. It is insoluble in water. Okay, basic compounds, they act just like ionic compounds. So what we're going to do is just treat them as soluble versus insoluble still. The only thing that separates them from an ionic compound is that a basic compound will always have OH negative hydroxide as its an ion, where it has a metal or a positive ion in front. Okay, looking at our solubility table, barium hydroxide is soluble. If it is soluble, that means that we can dissociate it into its ions. So we're going to get Ba 2+, which is aqueous, and hydroxides, which are aqueous. Now we have 2 hydroxides in our formula, therefore we need to balance with 2 hydroxides in our products. Our major entities, again, water is always listed. And our ions are separate, so if we were to zoom in on our solution, we would see barium ions, sorry, it should be a comma, and OH minus ions. Notice that I have put charges and states for everything. If you are missing a charge or missing a state, technically you are incorrect. Okay, so make sure that everything has a charge if it needs it, and states for everything. All right, acids. What we're going to do is we are going to look at them and consider them as strong versus weak. Okay, strong acids have a high degree of ionization, meaning when I put something like HCl in water, if I were to zoom in, all 100% of my HCl's are broken into H plus and Cl minus, all of them. Okay, approximately 100%, so like 99.9. So what we can say then is that they definitely ionize. They have an ionization equation. So H plus and Cl minus is what HCl will ionize into when we put them in water. Major entities, always listed, is water. And because if I were to zoom in, all I would see are these separated ions. My major entity will be H plus and Cl minus. Common strong acids, there's only 6 of them, so you have to memorize these. All right. So perchloric acid is HClO4. Hydroiodic is HI. Hydrobromic is HBr. Hydrochloric, obviously HCl. Sulfuric acid is H2SO4. And nitric acid is HNO3. These are the only strong acids. Every other acid is considered weak. So weak acids have a low degree of ionization and are poor conductors. So if we were looking at CH3COOH, what we know is that of 100 weak acid molecules, only about 1 of them will break into ions. So if I had 100 of these, only 1 is going to create CH3COO minus and H plus. All right, therefore I'm going to be left with 99 of these and 1 of each of these. Does it still ionize? Yes. Okay, so we are going to write an ionization equation for it. because we can write it as ions. Okay. However, if I zoom in on the solution and look for what is there, water's obviously there. And the major entity, what is there in the greatest quantity, is this acid still stuck together. So I'm going to say that the major entity is CH3COOH, and it's just dissolved in water. Okay, so aqueous. So that's the difference between strong and weak acids. Weak acids, the major entity includes the acid still stuck together, whereas a strong acid, the major entity includes the acid broken apart. Molecular compounds don't dissociate in water, ever. Okay, they will not create ions. The only molecular compounds that could were our acids themselves. So therefore, for any dissociation equation of a molecular compound, we will say that there is no equation for either of these. Doesn't matter what kind of molecular compound there is. Okay. The only thing that could change is the major entities. So we know water is present because I'm trying to dissolve everything in water when we're looking at these. If the molecule is polar, remember, like dissolves like. Polar things dissolve polar substances, and non-polar solvents dissolve non-polar substances. So because water is polar, it will only dissolve polar molecules. So in that case then, our molecule here, sucrose, will dissolve in water. Okay, we see that sugar dissolves in water. So if that's the case, C12H22O11 will no longer be solid. It is aqueous. Ooh-ah. However, it's not broken up into any ions. It is still a neutral molecular compound. Non-polar molecules do not dissolve in water. Okay, so any non-polar molecule will be written as its normal formula, C6H14, and because it doesn't dissolve, it does not become aqueous. It just keeps its regular state, so liquid in this case. There's a little table to try and summarize things here. You can go into the PDF notes to get a nice copy of this, but what we do to decide what's happening is decide what kind of compound it is. So we decide whether it was ionic, acidic, or molecular. When it was ionic, there were two considerations. Was it soluble or insoluble? For an acid, we had to decide whether it was strong or weak. For a molecular compound, we decided whether it was polar or non-polar. Again, maybe go take a look at the PDF to classify what happens for the dissociation equation and the major entities. For each of these, I'm not going to be able to write it very nicely here. Okay, and it just summarizes what we went through last few slides. The homework is not in the textbook this week. It is an assignment, PDF or Google Doc. So make sure you take a look for that